Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Instrumentation and Measurement. This is lecture number 5. Today we will discuss about the statistical characteristics, repeatability, tolerance, a method of calculation for the probability density function of error in the output, and we will do a solved example for a thermocouple which is connected with a 4 to 20 milliamps current transmitter. So the repeatability, it's a statistical variation in the output of an element with time, while tolerance is also the statistical variation, but it is among the batch of similar elements. To understand, we can assume that a single the output of the single element at different times, how repeatedly this is able to produce the output, and tolerance is about a batch of similar elements, and we see the output of the whole batch. This is about the tolerance. Repeatability, this is the statistical variation in the output of a single element with time. And suppose that the input I of a single element, for example, if we consider a pressure transducer, and the input is held constant at 0.5 bar. So if we take a large number of readings of the output, and we expect that the output should be 1 volt, it may not be. Always the 1 volt output. Sometimes the value may be 0.99, 1.01, 1, 1.02, and so. So what we obtained is the input is constant, and we made several readings, and we found that the output has a little variation. So note that the expected value was 1 volt, which is not obtained at every measurement. In this case, we can say that this effect is termed as lack of repeatability in the element. For good repeatability, the output should be consistently a single value. Repeatability is the ability of element to give the same output for the same input when repeatedly applied to it. And the lack of repeatability is due to several reasons, some random effects in the element or the environmental effects. So we can say that the lack of repeatability can be because of the random effects within the element, or it may be because of the random effects in the environment of the element. Now consider a vortex flow meter, and the fixed flow rate is 1.4 10 raised to the power minus 2 cubic meter per second, and the expected frequency was 209 hertz. But when we actually see, the fluctuations may be up to from 207 to 211 hertz. So the lack of repeatability is commonly due to the random fluctuations with time because of the IM and II, the modifying input and the environment interfering input from the environment. So if coupling constants are not zero, for example Km in this case and Ki in this case, then there will be some corresponding time variations in the output. So in this situation, like for example, if the ambient temperature changes and we are dealing with the strain gauge, the resistance will change, and the amplifier may change the output as well because of the temperature. And the random fluctuations in the power supply for a deflection bridge may change the output of the deflection bridge. So to control the overall system and have same quantitative idea about its behavior, we have to find out the variation quantitatively. So we need a little model. So with some reasonable assumptions, we can define or select some probability density function. Now the statistics will help us, and it will help us to mathematically represent the inputs I, Im and II, the variation in these, by using a function which is called probability density function. That this is the probability that the value of I will be within this range, or this value will be. So by this we can find the probability density function of the output. Now what will happen is we start from the input. So first we define the probability density function in the inputs, and then the variations in it, and we will use a mathematical model or procedure that will take us to the variation in the output. So we will be able to estimate the output. So first we start the probability or the estimation variation estimation in the inputs, and that will enable us to find the or estimate the variation in the output. So by making some reasonable assumptions, of course with some practical data, we will be able to make some assumptions and probability density function for the individual inputs which are causing the changes. For example, the variation in I, the variation in IM, the II, and the probability density function of the output can be found. The most likely probability density function for these inputs is usually Gaussian or the normal distribution, and there is a very proper reason behind that the real most of the real things or engineering systems or good engineering systems or the thing or nature is normal, follow the normal distribution or Gaussian distribution. The formula for the Gaussian distribution is this 1 upon sigma under 2 pi exponential minus x minus this is the mean value, expected value that we, and this sigma is the variation. So x bar is the mean or expected value. For example, here in case assume that this is the 100 ohm resistance that we expected, and we took around, for example, 1 2 3 4 5 6 7 8 9 10 11. So we took 11 resistors of 100 ohms, but they appear like this, that out of these 1 2 3 4 5 were having exactly 100 ohms, and 3 were having 2 were at 99 or 99.5, 1 was at 96, and there were 2 101 and 101 ohm resistors, and one was 104. So if you see, this is the deviation from the mean value, and if we plot it, a nice continuous plot will be, this is the normal distribution, this is the Gaussian normal distribution of the system, and it tells us the probability that this will lie within the range of minus sigma to sigma, and then there is a probability that the value will lie between minus sigma to plus 2 sigma, and then this is the probability that it will lie between minus 3 sigma to plus 3 sigma. Now there is a fact that will help us in moving towards the method by using the input variation in the input to the variation in the output. So the dependent variable y, assume mathematically y is a linear combination of the independent variables x1, x2 and x3. So if x1, x2, x3 have the normal distributions with the standard deviations of sigma 1, sigma 2 and sigma 3, so then the probability distribution of the y, which is the output, is also normal with the standard deviation sigma given by this function, which is in terms of the standard deviations of the inputs. So x1, x2, x3 are input here for us, and there we will find, if we are able to have the statistical model of x1, x2 and x3, then we will be able to calculate the statistical variation in the output. So this is the effect from the linear algebra that will help us, and the method says that so since we have this model, we will and we have 3 independent variables I, IM and II, so we can find the variation in the output with respect to each of them. So this is the slope or the sensitivity of output with respect to the input times the variation in the input, then this is the variation in the output with respect to IM, and this is the variation in the IM, and then this is the sensitivity with respect to the II, the change in output with respect to the input II, and this is the variation. So this whole will tell us the total variation. So this part is delta O1, which is the variation due to the input I. This is the variation in input M. This is the variation due to input M. This is the variation in output due to input II. So by using this, a linear combination of these variations can give us the standard deviation in the output. So this will be given by the individual. So sigma I is basically the standard deviation in the input variable. I This is sigma im is the standard deviation in the input variable im, and this sigma ii is the standard deviation in the input ii. So, and the average values for to formula, if we come back to this, if we directly to reach to this formula, we see we need the average value of the output. So the average value of output can be used by using the same equation 2.9, but replacing every value with its corresponding average value. Sensitivity will be the same. This I will be average value, O, then the nonlinearity be calculated at the average value, and im and I average value, and ii average value. So this will give us the average or mean value of the output, and using this formula and sigma naught we will calculate from 2.18. By using this formula we will be able to calculate the probability density of the error or output. So recall that I just went through this by hand. So this is the equation 2.9. If our delta O is a small deviation in O from the mean value O bar caused by the deviations delta I, delta im, delta ii from the respective mean values I bar, im bar, ii bar, then we can write the variation, the small variation, as a linear combination of these three. So delta O is a linear combination of the variables delta I, delta im, and delta ii, and notice that these are the corresponding sensitivities with respect to each input variable. Note that we can evaluate the above partial derivatives using 2.9. So it's an exercise that, okay, this was the equation 2.9, and you differentiate it with respect to I. So when you differentiate, the first element is ki, so this will be I will go, and this we will get k. Second is a, which is a constant, we will get 0. N is a function of I, so that's why there will be a derivative delta n I upon delta I, and km im I. So here we will be we will get km im, and finally there is no I here, so this will become 0. Similar, so this is the way the sensitivity with respect to I will be equals to this value. Sensitivity with respect to im is kmi, and sensitivity with respect to ii is ki, and you check by yourself as also. So if a dependent variable y is a linear combination of the independent variables x1, x2, and x3, the y can be written as a1 x1 plus a2 x2 plus a3 x3. This is the fact we just saw. And if x1, x2, and x3 have normal distributions with standard deviations sigma 1, sigma 2, sigma 3 respectively, then the probability density function of y is also normal with standard deviations sigma given by this. So this is the having this linear combination, we can find the standard deviation in the output as a function of the standard deviations of the input. So using the above algebraic fact, the previous one, and the combining the or mapping the equations 2.16 and 2.15, we will get this a1 is basically delta O upon delta I, and a2 is delta O upon delta im, a3 is delta O upon partial differential of delta output with respect to im, and sigma 1 is sigma I, sigma 2 is sigma im, sigma 3 is sigma ii, and this way we can write the the standard deviation of the output as this equation 2.18. So equation 2.18 is here it is. Now we have a standard deviation of the output of a single element as this equation, where the standard deviations of the inputs are given. Thus we will now move to calculating the average value. Alternatively, if a calibration test is being performed on the element, then sigma naught can be estimated directly. By the way, if for any of the elements, if this standard deviation is not given, we can do a calibration or perform some experiments to get and estimate this value. So the mean value of the output for a single element is given by equation 2.19, which is ki bar. So here for every input, and average value will be used here to calculate the average value of the output, and corresponding probability density function will be given by this equation 2.20. So now coming and reviewing the tolerance, it's the standard statistical variation among the batch of similar elements. Suppose that a user buys a batch of similar elements, for example a batch of 100 resistance temperature sensors from a manufacturer, then it measures the R naught for each one, and they may find, for example, the value is 99.8, 100.1, 99. So there is a variation in the resistance, and this effect is due to the small random variations in the manufacturing process, and the probability density can be given by this equation, where R naught is the mean value and sigma R naught is the standard deviation, which is typically 0.1 for a 100 ohm resistor. So a manufacturer may state that with this in his specification that R naught lies within 0.15 plus 1.15 ohm of 100. So at any time you should expect that the variation can be plus 100 plus 100 plus 0.15 or 100 minus 0.15. So thus, in order to satisfy these limits, you must reject all the sensors. Now once you have specified this, if the production unit is producing something beyond plus minus 0.5, that should be rejected. So this is like a quality control. So you will reject all of the values which are less than 99.85, and also reject all the values which are above 100.15 ohms. Okay, so this is only the satisfactory, provided that the tolerance is allowed and the user are okay with this tolerance, and the rest will be rejected. Now once you have when you have purchased this, you have two choices. You can design this measurement system. Either for example, you have these values. Either we assume the value of 100 ohm as R naught, and we design and expect that okay, there will be a value, some error in this, or we can perform a calibration test to measure R naught as accurately as possible for each element in the batch, which is theoretically to remove the error, but this is very time consuming and expensive, and might not be recommended. So this effect is found in any batch of identical elements. Statistical variations are found in the batches of thermocouples and thermistors, for example. Now basically what's happening is, in the general case, we can say that the values of the parameters such as the sensitivity K, we are talking about individual elements. For each individual element, like one resistor, there will be a K and the 0 bias A. So for each one, for a batch of elements, the K's and A's are distributed statistically. For example, the resistor 1 will be represented by K1 and A1. Resistor 2 is represented by K2 and A2. And there will be a little change. They may be same. A1 may be equals to A2, but it may change in A3. Will be a little different. So all of these the sensitivities constants K, linear sensitivity constants K, and the 0 bias A, they all will be modeled as K bar and A bar. So for example, for all of them, the K will be summed up and divided by the total number, and we will have average K. Similarly, the 0 bias of all the resistors will be calculated, and they can be represented by A bar. So this will be the average model of the whole batch. Now we will go to the examples, how to estimate the variation in the output of a measurement system. See here we have a thermocouple which is characterized by the nonlinearity and changes in the reference junction ambient temperature TA acting as the interfering input, and there is also a 0 bias is also changed. So if you see and with the 0 biasing, you see the mean value of A naught, which is the 0 bias, is 0, but the standard deviation of this is 6.93 10 raised to the minus 2. So there is a little variation in A naught in some of the elements. So this is a model equation. Thermocouple E T is the temperature that we want to know. TA is the reference temperature, equals to A naught plus A1 T minus TA plus A2 T square minus TA square. And we are reading it for measuring a temperature of from 50 to 150 degrees centigrade. So this is the model equation. Now statistically what's happening is, the mean value for A naught is varied, and the mean value is 0, but the standard deviation is this 6.93 and 10 raised to the minus 2. So there is the variation in A naught. Also the variation A1 parameters has 0 variation, no variation. A2 parameters, so A1 and A2 are like fixed, they have no values, no variations, while their mean value is 4.017 10 raised to the minus 2, and for A2 mean value is 4.66 10 raised to the minus 6. while the mean value of the reference junction is 10 degrees here, but there is still we have a small variation in of 6.7 as a standard deviation. Now to solve this, we will calculate the partial derivative as differentiate this with respect to a naught, differentiate it with respect to dA. All the parameters we have to differentiate it, and then we calculate the mean value, and from this we will be able to calculate the standard deviation of the output. Here is the MATLAB. I solved this in the MATLAB. Since we have the this value is given the partial derivative of the E with respect to a naught. This is 1, so we have 1 here, its power times then we have the standard deviation of a naught. This is sigma a naught is given here 6.93, and this is the value here. And notice that this is a square and this is sigma, so we put a square here, plus the partial differential of E with respect to dA. This is calculated here, minus 4.026 10 raised to the power minus 2, so we calculate it, we put it here, and then finally we have the standard deviation of dA, which is 6.7 times the square. So once you calculate this value, sigma square, the output of the thermocouple in the EMF, which is the output. So the variation, the standard deviation in the variation, the standard deviation of the output, which is the EMF of thermocouple, is equals to sigma square is equals to 0.0776, and this is and it is further connected to it is, so we have this value here. And then the transmitter is a linear, but is also affected by the ambient temperature. So this is the 4 to 20 milliamps current transmitter, which is represented in terms of the current is here I equals to Ke. This E is the output of the previous element, which is the thermocouple, plus Km E delta Ta plus Ki delta Ta plus A. So this is the mathematical model given for a 4 to 20 milliamps output, which is taking input as in millivolts of 2.02 to 6.13 millivolts input. Is designed, and delta Ta is the deviation in the ambient temperature from 20 degrees. So 20 degrees, whatever, if it varies plus or minus, the temperature will appear here. The mean values of this limit r k bar is given here, and the standard deviation in k is 0. The a bar of this model is 3.864, while the standard deviation in a is 0.14. Delta Ta bar average value is minus 10, and the standard deviation in delta Ta is 6.7. Km bar average value is 1.95 10 raised to the power minus 4, while the standard deviation of this Km is 0, and similarly Ki is 2 10 raised to the power minus 3, while the standard deviation is 0. So this is the statistical variation, mean value and the standard deviation of these all the input variables and the parameters. Next we do a partial differential of this whole equation, because I is dependent on all of them, parameters and inputs. So we differentiate it with respect to E, with respect to delta Ta, and with respect to A, but we don't differentiate it with respect to other K, for example. Why? Because the standard deviation is 0, so we will not differentiate it with respect to K, with respect to Km, with respect to Ki. If these values would have been some non-zero values, for example, if there is a non-zero value here, Km, we would we needed to calculate the partial differential with respect to K. So here the only three partial differentials are calculated only because there are only, these are the three non-zero standard deviations. Okay, so these are the three standard deviations we have not calculated, but if there are some non-zero values here, we would have calculated the partial differential with respect to these. Okay, moving towards the mean value. So the mean value of the output will be calculated based on the mean value of all the input parameters and their the inputs and the parameters, and then the standard deviation is given by in terms of their linear combination of the standard deviation and their partial derivatives. So delta I upon delta E is 3.891 here, and delta E is calculated in the previous section, which is 0.0776. This is, if you go back, This is delta E in the previous slide that we calculated, delta E, and this will come from there. Delta I upon the partial differential of with respect to delta TA is this 2.936, and the partial differential of I with respect to A is 1. The standard deviation of with respect of delta TA here, this is delta TA, it's I think not written here, but this is delta TA is 6.7, and sigma A is given here 0.14. So a MATLAB single line statement, I wrote here 3. If you see delta I, you can see this is the first value of partial differential, which is differential with respect to E, delta I upon delta E. This is the from the sigma E from the previous. If you see this is the same variable name, the sigma E square that I use in the MATLAB command. So this is sigma E underscore square, and then we have the partial differential with respect to delta A 2.936, and then we have 6.7 here, okay, and then we have the this is 1, delta I with respect to A is 1 here, and then 0.14 for sigma A, 0.14 this value here square, and this will give us 1.1943, and the sigma is calculated as 1.0928. So you see there is a variation in the output. It means that the zero and sensitivity of this element are adjustable. So K and A of this element are adjustable, and we cannot be certain that this transmitter is set up exactly as required. So there might be some tuning required, and it is not being properly calibrated or tuned, and this is reflected in the non-zero value of the standard deviation of these 0 bytes. So this should be this should have been 0, but 1.0928 mentions that there is some problem either in this element or the previous element, and we have to calibrate it properly. And this is all we have done with the some current data and the mathematical relationship and the estimation. So thank you very much. For any questions, please write me an email, which is on the first page. Thank you.